Hello. So yes, we've taken our first look at extended bodies by looking at moments and couples and torques. Now we need to get onto energy and momentum, because I mean, even if we've got an object that isn't being translated through space, it's got no linear kinetic energy or linear momentum. All other things being equal, if it's spinning round, it must have more energy. Two objects, two golf balls sitting there not moving, one of them's spinning, the other one isn't. Well, the one that's spinning has got more energy. So we need to build this into our descriptions of energy and momentum. So how are we going to go about doing this? So say we've got, well, let's go with a disk. We've got a disk, uniform disk, circular disk, and it's rotating about its center in a clockwise fashion with angular velocity omega. Now the energy that's in this disk will depend upon the mass distribution. We think of this disk being made up of lots of little points. Every little point has got some mass mi. Well, that point is moving around. It's at a radius of ri for that particular point. So it's moving with a velocity of, well, v is, remember from our circular motion, v is omega r. So a half mv squared will be a half mi ri squared omega squared. That's going to be the kinetic energy of one little bit of this disk spinning around. So the kinetic energy of the whole disk is going to be the sum of all of these, and that's why it's going to depend upon the distribution of the mass, because if you've got more of the mass close to the axis of rotation, well, it doesn't have to move as quickly to complete a circle. Everything's moving slower, you've got less energy. If this was just a ring of the same mass as the disk and all of the mass was at the circumference, everything's having to move quickly, you've got more energy. So rotational energy depends upon the mass distribution in the way that it doesn't for linear kinetic energy. When we have our linear kinetic energy, we're just doing a half mv squared. We don't care where the mass is distributed in the object because all of it is being translated in the same way through space. It doesn't matter where the mass is. We could have a great big hulking thing where most of the mass is in one corner and then it's sparsely gathered around there. Well, it doesn't matter how that's distributed because all of these points are moving at exactly the same velocity. So big whoop as to how it's distributed. Here it does matter because things further away from the axis are moving faster than ones close to the axis. Right, so to get the total kinetic energy, we need to sum all of this up. So our rotational kinetic energy of this disk is going to be the half omega squared, our constants, and then it's going to be the sum for all n little masses that we've got, so I from 1 to n, of mi ri squared. So that's what we need to work out for a calculation of the rotational kinetic energy. And this last bit here, this sum that we've got going on here, this is the thing that's varying from point to point. And if you compare it to the kinetic energy formula we got for linear motion, you can see, we've got the same half here. We've got an omega squared, we've got a v squared. So we're comparing linear velocity with angular velocity. So this bit that's left here, the sum, it's like our rotational mass. So this is the rotational mass of this particular object. It depends upon the shape of the object. And the sort of technical term that's used for rotational mass is moment of inertia. It's it's one of these old sounding, well, it is an old term that they came up with a long time ago to describe this rotational mass. So a large part of working out rotational energy and angular momentum and things like this is working out what is the moment of inertia of a particular object. Because once we've got that, we're fine. We can use that as our mass in the way that we do linear mass when we're looking at translation through space. Now we've got this idea of moment of inertia, we can start, let's go back and compare all of the information that we've got so far when we're comparing rotation and linear stuff. So say we've got, so what have we got here for linear motion, then we know we've got displacement, velocity, and acceleration. We know how these are all related to each other. We're differentiating by time as we move down, and we're integrating as we move back up again. We've got the same thing for angular motion. We've already looked at this when we were doing circular motion. So instead of all of this stuff being in meters, and we got meters per second, and meters per second squared, we've now got angle, which is all in radians. So we've got angle per second, radians per second. That's our angular velocity. So that's our theta dot, differential of theta with respect to time. And then we've got our angular acceleration, our theta double dot, or our omega dot. So we've got exactly the same things going on here for linear velocities and angular velocities. And now we're extending this into our energy and through the mass as well. So we've got for linear and for angular, we've got our masses. So we've got our mass in kilograms, and now we've got our moment of inertia, which, well, we can see the units here. We got kilogram meter squared on this, kilogram meter squared. So that's our linear mass and our rotational mass, our angular mass. Now we've got our kinetic energy as well. So for kinetic energy, we got a half mv squared. For angular, our rotational energy, we got a half m, I omega squared. So I is our rotational mass. So a half mv squared, a half I omega squared. So again, direct translation between the two things. Our linear force, F in newtons, and now we've got a moment in angular motion, which is in Newton meters. So we've moved from our just linear forces to moments. We've got momentum. We've got our linear momentum P, our mass times velocity. We've got our angular momentum, which sadly they don't seem to give a symbol to. There doesn't seem to be any consistent symbol that's used on this. But again, we've got a direct translation across. So instead of mv, we've got I omega, our mass and our velocity in the angular sense. And then for work done, the final thing, you think work done, force times distance, that's our change in energy. And then in angular motion, instead of force times distance, we've now got the moment. Let's call that c. Multiply, instead of distance, we've got theta. So c times theta, that is our change in energy. And we saw this as well when we were talking about moments. That change in energy that we've got when we apply a moment. So our the moment is whatever the force is times that distance, if that's perpendicular, or we're taking the perpendicular distance. So we've got F times X is our moment. So that's the force, and then the distance is we're going through an angle of theta. No, the force that I'm getting my things the wrong way around. The distance that the force is being applied through, that arc of a circle, if we're rotating this in a circle through an angle theta, and that arc length is x times theta. So work done, force times distance, fx theta. So we've got direct relationships between all of these things from a linear sense to an angular sense. We're just switching from meters to radians, and we're switching from mass to moment of inertia. So the next thing that we have to do that brings all of this together, and this will be in the next video, how do we calculate moment of inertia for different shapes? And of course, this is going to be an exercise in calculus because we're going to have to solve this sum. So for continuous shapes, whether they're surfaces or volumes, we're going to be doing integrals. If you've got discrete points, a collection of objects which are held in some way or whatever, and they're rotating, we could just add them up. But by and large, we're looking at things like discs and spheres and rods and rings and things like that. So we're going to need to work all of those out. But yes, it's a nice relationship between all of these because you don't really have to learn anything particularly new in order to get all of the angular equivalents of the linear stuff. You just have to flip over a different measure of mass, different measure of velocity, and the fact we're looking at moments rather than just linear forces. And then the whole lot is there. It just drops out with exactly the same set of formulae. So yes, it's quite easy to get started on all of this.